Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on group lecture number 74, in which I will solve some problems on solvable groups. Now we solve a problem. Problem is so that symmetric group S4 of degree 4 is solvable. Now we solve this. Since the symmetric group S4 contains 24 number of permutations. Let A4 equal to set of all even permutations of symmetric group S4. This is called alternating group. Since order of A4 equal to 12, also A4 be the normal subgroup of symmetric group S4. Therefore, quotient group S4 by A4 exists. Now, order of quotient group S4 by A4 equal to order of S4 by order of A4 equal to 24 by 12 equal to 2. Since we know that a group of order 2 is abelian. Therefore, quotient group S4 by A4 is abelian. Now, V4 equal to a set containing elements row 0 be the identity permutations of S4 1, 2, 3, 4 permutation, 1, 3, 2, 4 permutation, 1, 4, 2, 3 permutation. Therefore, order of V4 equal to 4. Here we have 4 elements. 1, 2, 3, 4. Since V4 is a normal subgroup of A4, therefore quotient group A4 by V4 exists. Order of quotient group A4 by V4 equal to order of A4 by order of V4. Order of A4 is 12, order of V4 is 4. This is equal to 3. Since we know that a group of order 3 is abelian, therefore quotient group A4 by V4 is abelian. Let this is number 1, this is number 2, this is number 3, and this is number 4. Since the set containing only identity permutation is a normal subgroup of V4, therefore quotient group V4 by the set containing identity permutation exists. Since order of the quotient group V4 by set containing identity permutation equal to order of V4 by order of the set containing identity permutation equal to 4 by 1. This is equal to 4. Since we know that a group of order 4 is abelian, therefore quotient group V4 by set containing only identity permutation is abelian. This is number 5 and this is number 6. From 1, 2, 3, 4, 5 and 6, we get that the series here we write S4, here A4 is a normal subgroup of S4, V4 is normal subgroup of A4, and set containing only identity permutation is a normal subgroup of V4 is a solvable series. Therefore symmetric group S4 is a solvable group. Proved. Now we solve the next problem. Problem is prove that a subgroup of a solvable group is solvable. Now we solve this solution. Let G be a solvable group. Therefore G equal to G naught, G1 is a normal subgroup of G naught, G2 is a normal subgroup of G1 and dot 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 Gn is a normal subgroup of Gn minus 1, and let this is a set containing only identity element, and quotient group Gi by Gi plus 1, I equal to 0, 1, 2, dot 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 n minus 1 is abelian. Let this is number 1. Let H be a subgroup of group G. Now let Hi plus 1 equal to H intersect Gi plus 1, implies that Hi plus 1 is subset of H, and Hi plus 1 is subset of Gi plus 1. Let this is number 2 and this is number 3. Since Gi plus 1 is a normal subgroup of Gi, therefore Hi plus 1 is subset of Gi plus 1 is subset of Gi. Let this is number 4. From 2 and 4 we get Hi plus 1 is subset of H intersect Gi, implies that Hi plus 1 is subset of Hi. Since H intersect Gi equal to Hi, since Hi equal to subgroup H intersect a normal subgroup Gi, implies that Hi is a normal subgroup of H. Since Gi is a normal subgroup of G, therefore quotient group H by Hi exists. This is number 5 and this is number 6. This is number 7. Since H is a subgroup of G and Gi plus 1 is a normal subgroup, therefore from 2 Hi plus 1 is a normal subgroup of H. This is number 8. Since Hi is subset of H Then from 6, 7 and 8 we get Hi plus 1 is a normal subgroup of Hi. This is number 9. Therefore, quotient group Hi by Hi plus 1 exists. Now, let F is a mapping defined on Hi to Gi by Gi plus 1, defined by Fx equal to x Gi plus 1. Let this is number 10. For x belongs to Hi, and since Hi is subset of Gi, implies that x belongs to Gi, implies that left coset x Gi plus 1 belongs to quotient group Gi by Gi plus 1. Let this is Hi and this is quotient group Gi by Gi plus 1. For element x, we get image x Gi plus 1. Therefore, F is well defined. Now, to show F is a homomorphism, let x, y belong to Hi, implies that x operation y belong to Hi, since Hi is a normal subgroup, implies that Fxy equal to xy Gi plus 1. This equal to x Gi plus 1 operation y Gi plus 1. Since Gi plus 1 is a normal subgroup, this equal to Fx and this equal to Fy. Let this is number 11. Therefore, F is a homomorphism. Now, to find kernel of F, since Gi plus 1 be the identity element of quotient group Gi by Gi plus 1. Here Gi plus 1 be the identity element. Now let x belongs to kernel of f, double implication, fx equal to identity element gi plus 1. Double implication, since fx equal to x gi plus 1, x gi plus 1 equal to gi plus 1, double implication, x belongs to gi plus 1. Let this is number 12. Since x belongs to hi and hi is subset of h, this is number 13. From 12 and 13 we get x belongs to h intersect gi plus 1, implies that x belongs to hi plus 1. This is number 14. Therefore, kernel of f equal to hi plus 1. This is number 15. Now let this is hi and let this is f hi, means collection of all image of hi. Here kernel of f equal to hi plus 1. Since the mapping f defined on hi to fhi is onto, and since f is a homomorphism, kernel of f equal to hi plus 1. Therefore, from fundamental theorem of homomorphism, or first isomorphism theorem, here we write quotient group hi by kernel of f is isomorphic to fhi. Hi quotient group hi by kernel of f is isomorphic to fhi, implies that hi by kernel of f is hi plus 1 is isomorphic to fhi. Let this is number 16. Since fhi is subset of gi by gi plus 1, since fhi is subset of quotient group gi by gi plus 1 and Gi by Gi plus 1 is abelian, since G is a solvable group. Therefore, FHI is abelian. This is number 17. From 16 and 17, we get that Hi by Hi plus 1 is abelian. This is number 18. Therefore, we get a series H. This is equal to H naught. H1 is a normal subgroup of H naught, since we know that Hi plus 1 is a normal subgroup of Hi. H2 is a normal subgroup of H1, and here Hn containing identity element, in which Hi plus 1 is a normal subgroup of Hi, and quotient group Hi by Hi plus 1 is abelian. This is number 19, this is number 20. Therefore, the series 19 is a solvable series. Hence, H is a solvable group. So, any subgroup H of a solvable group G is solvable. Proved. Now we solve the next problem. Problem is, if G is a group and N is a normal subgroup of G, such that both N and G by N are solvable, then prove that G is solvable. Now we solve this. Given that G is a group and N is a normal subgroup of G, therefore quotient group G by N exists. Also, given that N and G by N are solvable, G by N is solvable, implies that we get a series G by N equal to G naught by N G1 by N is a normal subgroup of G0 by N. G2 by N is a normal subgroup of G1 by N, and in this way we get G by M by N equal to set containing identity element, that is N, and quotient group Gi by N by Gi plus 1 by N is abelian. Since by third isomorphism theorem we know that Gi by N by Gi plus 1 by N is isomorphic to Gi by Gi plus 1. Let this is number 1, this is number 2, and this is number 3. From 2 and 3 we get here, this is abelian, left side is abelian, therefore right side is abelian. Gi by Gi plus 1 is abelian. This is number 4. Since Gm quotient group by N equal to set containing element N implies that Gm equal to N. This is number 5. Since given that N is solvable, therefore we get a solvable series N equal to N naught. N1 is a normal subgroup of N naught, N2 is a normal subgroup of N1, and dot 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 dot, lastly the set containing identity element, and Ni plus 1 by Ni quotient group is abelian. This is number 6, this is number 7. Since each Gi plus 1 by N is normal subgroup of G by N, here I equal to 0, 1, 2, dot 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 M minus 1. Therefore, Gi plus 1 is a normal subgroup of G. Since Gi plus 1 is subset of Gi and Gi is a normal subgroup of G, therefore Gi plus 1 is a normal subgroup of Gi. I equal to 0, 1, dot 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 A minus 1. And using 4, 6 and 7, we get a solvable series. G equal to G naught. G naught is superset of G1 and G1 is normal subgroup of G naught. G2 is normal subgroup of G1 dot 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 Gm, and that is N. Gm equal to N from 5, and this is equal to N naught. N1 is normal subgroup of N naught, and dot 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 dot, lastly set containing identity element. Therefore G is a solvable group. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.